All right, we're about to tackle the biggest story ever told. And I'm not kidding. It's the story of literally everything. The universe, our planet, and how you, right now, ended up in this exact spot. It's a journey that stretches across billions of years, linking cosmic explosions to the very ground beneath your feet.
So, let's start with a really simple question. Right now, where are you? You might say your city, maybe your country, or, planet Earth. But to get the real answer, we've got to zoom out. Like way, way out.
Because the truth is, you're on this tiny speck of rock orbiting a pretty average star, which is just one star in a galaxy of 100 billion stars. And that galaxy? It's just one of hundreds of billions of galaxies out there. The story of how you got here, well, that's the story of everything.
And our story has a definite beginning. We're talking 13.7 billion years ago. Everything you see, everything you are, everything that has ever existed was crushed into a single point, infinitely hot, infinitely dense. And then, poof, everything changed.
That moment is what we call the Big Bang. Now, it's a bit of a tricky name because it wasn't really an explosion in space. It was the explosion of space itself.
So the theory goes like this. This tiny ball expands violently, and for the first 300,000 years or so, the universe is just this crazy hot soup of particles. But as it keeps expanding, it starts to cool down, enough for the very first atoms to form. And the most amazing part? That expansion that kicked everything off, it's still happening, right now.
Now, people didn't always buy into this idea. For a good while, the competing steady-state theory suggested the universe has kind of always been here, just humming along, unchanging. But then, back in 1920, an astronomer named Edwin Hubble found proof that other galaxies are actually moving away from us. And the further away they are, the faster they're speeding off. That was the smoking gun for an expanding universe and a huge win for the Big Bang model.
So as the universe kept on expanding and cooling, gravity started doing its thing. It began pulling all that brand new hydrogen and helium gas into these massive clouds. And inside these cosmic nurseries, the universe's creation engines flickered to life, stars.
Every single star has its own life story. It starts out as a nebula, basically a giant cloud of gas. Gravity pulls it all together, tighter and tighter, into a hot, dense ball called a protostar. Once the core hits a blistering 10 million degrees Celsius, boom, nuclear fusion ignites. That's when it becomes a main sequence star. But eventually, the fuel in its core, the hydrogen, starts to run out, and the star swells up into a massive red giant.
Okay, so our star is now a big, puffy red giant. What's next? Its entire fate, its whole destiny, comes down to one critical number, 1.44. This is called the Chandrasekhar limit, named after the brilliant scientist who figured it out. It's exactly 1.44 times the mass of our own sun.
And here's where it gets wild. If a star's core is below that 1.44 limit, it fizzles out. It collapses into a superdense white dwarf and just kind of cools off over billions of years. But if the core is above that limit, its death is one of the most spectacular events in the universe. It explodes in a supernova, a blast so bright it can outshine its entire galaxy for a while. And this is where you come from. The iron in your blood, the calcium in your bones, pretty much every heavy element that makes you you was forged in the heart of an exploding star just like this.
And after that incredible supernova, for the absolute biggest stars, the story isn't over. The core just keeps collapsing and collapsing and collapsing until it becomes an object so dense, with a gravitational pull so powerful that nothing can escape it. Not a planet, not a star, not even a beam of light. A black hole. These things are the final, mysterious fate of the true giants of the universe.
So, from all those ancient star explosions, the heavy elements needed for planets and for life got scattered all across space. About 4.6 billion years ago, one of those clouds came together to form our sun and its family of planets. So, let's bring it in a little closer to home, shall we?
You can think of our solar system as having two very different neighborhoods. First, you've got the inner planets, Mercury, Venus, Earth, and Mars. These are the terrestrial planets, small, rocky worlds. Then there are the outer planets, Jupiter, Saturn, Uranus, and Neptune. These are the Jovian planets, the gas giants. They're absolutely huge, made of gas, and they have tons and tons of moons.
Okay, I know what you're thinking. What about Pluto?
Everybody asks about Pluto. Well, back in 2006, the International Astronomical Union basically laid down some new rules for what makes a planet a planet. And a big one is that a planet has to have cleared the neighborhood around its orbit. That means it's got to be the big boss, gravitationally speaking. Pluto, well, it shares its orbit with a bunch of other icy objects out in the Kuiper Belt, so it got reclassified as a dwarf planet. Sorry, Pluto.
All right, let's zoom in one last time. From the vastness of our solar system right down to our one-of-a-kind home, Earth. We know the surface pretty well, right? Oceans, continents. But what in the world is going on deep inside?
I mean, that's a real puzzle. The deepest hole we've ever managed to drill is only about 12 kilometers deep. The center of the Earth is more than 6,000 kilometers down. So how can we possibly know what's there?
The answer, believe it or not, comes from earthquakes. Yeah, when an earthquake happens, it sends these shock waves, seismic waves, rippling through the entire planet. It's like the Earth is giving itself an ultrasound. We can measure those waves on the other side. Now here's the clever part. One type of wave, called an S wave, physically can't travel through liquid. And we discovered that at a certain depth, those S waves just stop.
And that seismic data gives us this amazing picture of Earth's interior. We're living on the crust, this super thin, brittle shell of rock. Below that is the mantle, a massive layer of hot, dense rock that flows like super thick honey. And then we hit the core. That shadow zone where the S waves disappear tells us there's a liquid outer core made of iron and nickel. And right at the very center, a solid inner core squeezed solid by unbelievable pressure.
For most of human history, we just assumed that the continents were fixed, that the map of the world was set in stone. But then, in the early 20th century, a scientist came along with a completely radical idea. What if the continents themselves were moving?
His name was Alfred Wegener, and he was like a detective laying out his case. He said, look, the coast of South America fits perfectly into the coast of Africa, like a jigsaw puzzle. He found identical fossils and rock layers on continents thousands of miles apart. But there was one huge problem he couldn't solve. What kind of force could possibly be powerful enough to move entire continents? His idea was rejected for decades.
But Wegener would have the last laugh. The final piece of the puzzle, the evidence that proved him right, was hiding in a place no one had ever really explored before, the bottom of the ocean. It turns out the Earth's crust isn't one solid piece at all. It's broken up into these enormous tectonic plates that are basically floating on the gooey mantle below. And deep inside the Earth, the intense heat from the core makes that mantle churn in these huge slow-motion circles, kind of like a lava lamp. These are convection currents, and they act like a giant conveyor belt, dragging the plates along for the ride. This was the powerful engine that Wegener was missing.
And here's the thing. This process is still happening. Right now, North America is moving away from Europe at about the same speed your fingernails grow. This entire story, from the Big Bang to the shifting continents, is a story of constant, unstoppable change. Which leaves us with one final, mind-bending question. If this is what our planet looks like today, what will it look like in 250 million years?